Hi, everyone. I'm Michael Saxon, a PhD student at UC Santa Barbara, and this is my work with collaborators from ASU and Johns Hopkins called Lost in Translation, Translation Errors and Challenges for Fair Assessment of Text-to-Image Models on Multilingual Concepts. So what do I mean by multilingual assessment in text-to-image models? This is a follow-on work on some previous research that we had done before, where we inspected the multilingual capabilities, in particular unexpected multilingual capabilities in text-to-image models. What we did in this work was we produced parallel lists of prompts describing common tangible objects, in this case, a photo of an airplane, and then we would slot in different text-to-image models, such as Stable Diffusion, DALL-E, etc., and then prompt them with these parallel translated prompts. These would give us populations of images for each of these concepts, which we could then use some image space features to check if the model truly knows those concepts in the different languages. In order to produce this set, we sampled sets of tangible nouns, mostly in English, and then applied this rather convoluted pipeline to translate them into these parallel lists. In order to do this, we first used an ensemble of commercial translators such as Google Translate, Baidu, etc., produced candidate sets of translations from those different translation systems, and then we used BabelNet, which is a knowledge graph produced from Wiktionary and other sources that ties together these things called SYN sets, which are single semantic parallel sets that are aligned to the same meaning. The idea in this implementation that we had was that we could use these parallel SYN sets in order to assert that the same sense of the English word was preserved across these translations. So, I could have used these to explain. So here's the initial list of concepts. There's our translation pipeline, and then we end up with these parallel translated lists. What this allowed us to then do is feed each of those translated concepts into these different models. So we have, going from top rightward to bottom, we have DALL-E Mini, DALL-E 2, CogView 2, which is a Chinese language model, Stable Diffusion 1.4 and 2, and Alt Diffusion, which is a model that was explicitly trained using a multilingual encoder rather than CLIP. These histograms represent each of those concepts in the inventory that we had collected using that translation pipeline. Rightward mass corresponds to a higher concept level cosine similarity in the image feature space between the English language images and the other language images. What this represents is that for each of those languages, more rightward mass means that more concepts are known by those models, whereas leftward mass means that the model is less performant in those languages. So here are some tangible examples from that initial work. So here's DALL-E 2 being fed the concept of airplane in each language. As we can see, for Chinese, it does appear to know the airplane, although between the different languages, there are some nuances and difference in what the prototypical image of an airplane would look like. However, when we go to Stable Diffusion 2, while it still knows what an airplane is in Spanish and German, it does not know it in Chinese. We verified that this work was correct by checking from these histograms and sampling from the rightward side, by checking against what the concept itself was, and that x-axis correctness feature, which we called XC, we were able to indeed verify that these concepts and these features do correspond to knowledge of the concepts by the model. So we have from top to bottom, Spanish rabbit, Japanese snow, and Indonesian guitar. And just by sampling from these histograms, we indeed confirmed that this is a proxy for knowledge. However, when we presented this work to my future collaborators at ASU, we found that there were actually quite a few errors in this translation set that we had produced. In fact, what we found was a candidate error rate of 4.7% in Spanish, 8.8% in Chinese, and 12.9% in Japanese. However, we were as picky as possible with calling something an error. So for example, on the top row, we have an error for the translation of the concept bike into Japanese. The original translation produced by the model was baiku, which has more of a sense of a motorbike than a bicycle. This is a difference in the prototypical sense that English speakers and Japanese speakers would have for a bike. Whereas under the candidate correction, when we translate it to jitensha, we indeed are able to verify that now the images are the same between English and Japanese. However, we wouldn't necessarily characterize that as a particularly severe translation error. Whereas on the bottom, we translated the concept suit under this system first to 适合, which means suitable or fitting. However, when we applied the translation to 西装, it now means a Western suit, and the images are correctly generated. So the question is, which of these translation errors really matter? Which ones impacts the construct validity of our data set, and which ones don't? So we introduced this text domain error severity feature, which we called delta sem. What we did was we used a multilingual embedding space for the concepts before and after correction, and then we look at the difference in distances between those words in English and the candidate language in the embedding space. So here's that same example of bicycle, where we have baiku and jitensha. They're relatively close together in this embedding space as they share a lot of senses. It's a small difference and therefore a small delta sem. Whereas another translation error, which we had in Chinese, was we translated the word table into biao, which more means like table as in a spreadsheet, as far as I understand. I don't actually know Chinese. I just made sure to take note of how to pronounce these before the talk. However, when we applied the correction to 桌子, that is much closer to the prototypical sense of a tangible table that we have in English. Now, of course, these are both correct translations for the term, but it doesn't really make sense to ask for an intangible table as a tabular form into a text-to-image system. So we do characterize this as a large difference and a severe error. So we first use this delta sem feature and look at each of the translation errors. We identified a few different error types, which we referred to as formality. An example of that would be translating the word father into a sense that more means daddy or papa instead of a sense that more closely aligns to the level of formality that father has in English. We also have commonality errors, where the word was translated to a less common but still technically correct version of the term. As you can see, we have this gradient from relatively questionable if it really counts as an errors. And another example of that would be transliteration errors. So one example is the word flame. When we translated flame into Spanish, a common translation of that is llama, L-L-A-M-A. Now, that is a correct example of flame, but it has a collision in English with the word llama. So that is what we call a transliteration error. And then finally, we have sense errors, which are the most severe. So as we can see on these plots, the IS and OS colors, the darkest ones, are much more rightward on our delta sem feature, as opposed to the formality and commonality, quote unquote, errors. So the question is, does this delta sem feature predict which translation corrections will actually improve the performance of this benchmark in the image domain? In order to assess that, we test the change in that delta C, the aforementioned x-axis feature characterizing the knowledge of a model of each individual concept against that delta sem. So here are the examples of that correlation for Stable Diffusion 2.1 for Japanese, Chinese, and Spanish, going from left to right. Now, from inspecting these plots, it doesn't really look like this delta sem feature is predictive, except for in the case of Spanish. However, we can tie this back into the analysis done in the previous paper. So these are the histograms, once again, for concept correctness, and I've highlighted in green the rightward side of the concept mass. As you can see from this analysis, English, Spanish, and German have considerable rightward mass. So it would be reasonable to say that this model has more knowledge of Spanish and German than it does of the other languages. By contrast, alt diffusion here has considerably more knowledge of Chinese and Japanese. So indeed, when we, once again, I could have used those to illustrate, but the point is, when we check alt diffusion for these same scatter plots, we now find there is a very considerable correlation. So in other words, this basically confirms what we had expected, that there is this strong correlation between these two similarities in both the text domain on the x-axis and the image domain on the y-axis. So here are some subjective examples here. In the case of tent, this is a strong example of a commonality error. So in Spanish, you can technically translate tent as tienda. Now, tienda also has a collision with the word shop, because I guess in old times, shops were often put under tents. And indeed, when we translate tienda into shop, it actually works on Stable Diffusion 1.0 and 2 to give us a shop rather than a tent as we had expected. Similarly here, for the more severe error on the right, when we translate table to biao, we don't get meaningful images. It's just nonsense. And even after we correct it though, it still doesn't work. That's because we are looking at these models that do not have much Chinese knowledge. However, by contrast, when we look at these models that have more Spanish and Chinese knowledge, now applying the corrections does help them, as you can tell from looking at the bottom row, where tienda, under the correction, tienda de acampar, which literally means tent for camping, does indeed give a tent that is aligned with the English sense. Similarly, the correction that we applied on Chinese now does produce a table that is quite visually similar to the table that was generated by that model in English. So what are the implications of this work? First off, there's the pretty obvious ones, which are that we should apply these translations to our benchmark. So we've gone ahead and done that. We applied all of these changes that had a high delta sem into our new version of our Coca-Cola benchmark, which is what it's called. That stands for conceptual coverage across languages. And in future versions of the benchmark, though, because we don't really want a manually produced benchmark, we want a dynamic benchmark generating process, we need to do better with our translation pipeline. This issue really boils down to the fact that translating a single word into a specific sense is quite out of domain for translation models. They're meant to translate full sentences, and the ambiguity that's inherently present in a single word where we're looking for one specific sense is very difficult for translation models to overcome. We found that from preliminary experiments, working with LLMs to do this is quite promising, and in future versions, we plan to do so. But then there's these higher level questions that really are present in any kind of work inspecting multilinguality in any kind of model, not just text-to-image models. First of which is that not all concepts even are translatable. Now, in our previous work, because we focused on common, tangible concepts, this really wasn't much of a challenge. But if we want to push this further and really test the parity of multilingual knowledge in models, we're going to have to overcome this challenge. The next question is, what really are the limits to multilinguality assessment in general? Because there's more to multilinguality than just having parallel alignment between English and the test languages. Really what we need is a way to verify that the performance of the model in the language is meeting the speakers of that language on their own terms. And while we are able to test for parity, figuring out a good grounded way to test for the second question is much more difficult. And if we want to scale this assessment more, how do we find those prototypical concepts that do make sense to translate? And finally, are there ways to assess that knowledge that doesn't require this strict sense and translatability agreement, as we relied on in this work? All of these are really important questions that I hope to work on, and I hope to see some of you work on as well. So thank you. And if you have any questions, you can contact me at that email.
Hey, I really enjoyed this talk. Thanks a lot. And I have to say, I'm impressed by your Chinese pronunciation.
I'm much better at pronunciation than comprehension.
I have a question. About do you think it's possible to apply this framework to the more abstract concepts such as happy, sad, or events, such as using not only image but perhaps a video, a very short video, to describe what this event looks like?
Yeah, that's a great question. So as far as the video issue, I think that boils down to just a general assessment capacity that's much harder than tangible concepts, which is looking for verbal knowledge. So I know in the example of using clip, so I mean, I can back up a little bit. The way that this system is really working is that we're using the clip features in order to compare the generated images. Now, clip has a lot of, sorry, this is going to take a, okay, here we go. Clip has a lot of issues with performing these tasks beyond just tangible concepts, because the objective that Clip was trained on is doing this contrastive learning between specific images and then their captions. Now, the problem is that those mini batches don't contain hard examples beyond just using the nouns, right? So maybe there's one image of a panda in a tree with that caption, but then all the other images in that mini batch are just completely unrelated. So all that Clip had to learn is to attend to the tangible objects, which is why it's the easiest thing to assess. We've been experimenting with trying to measure things like verbs and attributes. So trying to say, like, for example, and also relations. So like, for example, can we test the relation on fire within the different languages? It turns out that that is quite difficult because really it's just attending to a fire. So if there's a fire in the image, but it's not the object itself actually being on fire, these features are blind to it. And additionally, this was something that I elided, but we cover in the paper. With this bike example, even though this motorbike and bicycle senses are very close together, Clip is actually blind to this distinction. So because there are two wheels and a person sitting on it and a seat and handlebars, Clip doesn't really care about the nuanced differences that one is a motorcycle and one is a bicycle. So in general, those are really big challenges, and I think they require modeling advances to automate them.
Thank you.
Yeah, thank you. Any other questions?
William Wang from UCSB. I have a question about the your suggestions for the future, data set. So can you give us some, hints about how do we actually take this into account for building future data sets? Thanks.
Sure. Yeah, that's a good question. Thanks for setting me up, William. So here was the diagram where I was showing how to generate it. And like I said before, what we had hoped would help us overcome these word sense errors by using this knowledge graph to align the differences actually didn't protect us. And in some ways, it actually made the errors even more severe. So an example that I didn't cover in here, but is in our paper, is that actually across all the languages, when we translated rock, it translated it to mean rock music rather than rock as in a stone. And this error was actually propagated by our use of a knowledge graph for agreement. What we've been working on now to try to improve this is using an LLM. GPT-4o is actually quite good at performing this tangible domain translation task. And even in cases where it isn't, we're actually able to, once again, use those ensemble of commercial translators, but then use a LLM as a verification in the follow-up. As for scaling it, beyond just tangible concepts, like I was saying before, use of the LLM and not having to rely on this knowledge graph allows us to scale beyond these high resource languages into more low resource ones, because the LLM, particularly GPT-4o, has picked up sufficient capabilities on many languages in order to translate them. So we're hoping to scale in that way. And finally, like I alluded to before, we're actively working on better metrics, mainly using VLMs, to compare for these more abstract concepts, relations, and verbs. So look forward to seeing that, hopefully by the end of this year.